Today I'm going to talk about our second biomolecule, which are lipids. So I've already talked about carbohydrates. In another video I'll talk about proteins and a different one, nucleic acids, but this one's all about lipids. There's a couple different types of lipid molecules, and it's a little less like the structure of polymers like we talked about before. Polymers are these long chains of repeating individual units that are called monomers, and lipids have a lot of characteristics that are in common with each other, but it's not necessarily a long chain molecule in the same sense that has all those repeating units. So lipids are a little bit more unique, but they do have fairly recognizable features. So we're going to talk about two different classifications: fats, which are used for long-term energy storage and heat, and signaling molecules, which are hormones, which come about because of steroid molecules, and steroid molecules are lipids as well. So let's talk a little bit about fats and how they're made. You've probably heard of the molecule glycerol, especially in the context of soap, and we'll kind of talk about why that is in a second. Glycerol looks like this. It's 3 carbons, and each of the carbon has a hydroxyl group on it, those alcohol groups. And so this is a molecule of glycerol. And when a molecule of glycerol reacts with 3 what are called fatty acids, and the reason that they're called fatty acids is because of this feature right here. This feature right here is called a carboxylic acid. Carboxylic acid. It's a functional group with a carbon that's double bonded to an oxygen, that's that carbonyl, attached to an alcohol group. And so this carboxylic acid is on one side, and this hydrocarbon tail is on the other side. So these are just carbon to carbon bonds with hydrogens. So carboxylic acid on one side, fatty chain on the other side, hydrocarbon chain. And so if we have 3 of these fatty acids, then they can do this chemistry with these guys to where the hydrogen and 2 and our hydroxide for each of these guys is going to react together, and it's going to make 3 water molecules that come out. So it's kind of a dehydration reaction. We're losing water molecules and forming this bond, and so we end up with a fat molecule that looks like this when I put it all together. So it's all one piece. Okay, so I had kind of the glycerol and the 3 fatty acids. We removed all that water, and then I ended up with this molecule that is now bonded together with the oxygen, and the water has left. Now, while we're talking about this, fat molecules and oil molecules tend to be somewhat used interchangeably, but fat usually refers to the fact that it's coming from animal sources, and oils are usually from plant sources. Okay, so you can probably think of some examples of that. Fats, like the fat that's in steak, if you're picturing that. If you're trimming the fat off a breast of chicken, for instance, or whatever, then that's usually an animal reference. Whereas oils, we talk about olive oil, we talk about almond oil, avocado oil. Those are all plant-based. And they're the same molecule. There are some features that are not in common, but we'll talk about those in a second. But this is just the general trend. There is an exception to oils. There is an animal that contains oils, and that would be fish. You've probably seen fish oil tablets or have taken them before. They are quite fishy, and you get a bunch of essential amino acids from that, and essential fats from that as well. So there's those omega-3 and omega-6 fatty acids, and you find them both fairly plentifully in fish oil. Okay, so that's just a terminology piece to this. Now you'll see that in my fat molecule here, all of my carbons in my hydrocarbon chains, so all of these carbon to carbon bonds are all single bonds. So we said when we were talking about organic molecules that when we have all single bonds, that those carbons are saturated. So we call this, because of the saturation of my carbons here, a saturated fat. So it's all single bonds in those hydrocarbon chains. And saturated fats, if you think about some examples of saturated fats, a saturated fat would be something like butter, or lard, And if you're thinking about saturated versus unsaturated, then saturated fats tend to not be as good for you. And you'll notice that if we just think of those two examples even, that these are both solids at room temperature. And the reason for that is because of their molecular structure. If you look at these straight chain hydrocarbons, these singly bonded molecules, this is a giant molecule put together. And if we have a bunch of these together, they're all going to stack on one another, and they're going to compress and stack really well. And because they stack so well, they tend to be solids at room temperature. Now think about what those would do in your body then. If you have a bunch of these things that stack really well, and now they're in your arteries, and now they're trying to move around in your body, and you get these chunks of them together, these solids that are forming, then you get problems. And that's why too much saturated fat is a bad thing in our diets. Now, if we have unsaturated fats, that would mean that there's carbons in here that have double bonds. So it might look something a little more like this. And I'm going to draw my more of a skeletal diagram here. So this is still my glycerol backbone, carbon, carbon, carbon. There's my oxygens. My double bonded oxygen there. Now, if I look at the hydrocarbon chain that comes off of this, if there's a double bond here, then that's going to cause a bend or a kink in this hydrocarbon chain. Or if I have one that goes like this, and then there's a double bond here, it's going to cause a kink in the chain up this way. If I have one here, it's going to cause a kink in the chain. Okay. Now, when we talked about isomers around double bonds before, we said that this really hinders the movement of these tails. So I can't just bend this and straighten this out, just naturally occurring. It's going to stay this way because I can't just rotate it freely around that double bond. And if we look at the way that the directionality of these, then the bend on these things, the kinks in the chains, are happening because each of these double bonds likes to be in the cis conformation. Okay, so these are all in the cis conformation, which means same. And that's what naturally occurs, that they will form with the cis conformation. And that causes this bend or these kinks in the chain. And because of these bends in the chain, and because of these double bonds in general, we just say, well, this is an unsaturated fat. Unsaturated because of the double bond, and because it doesn't now stack as well, and you can kind of even see this, it's not going to stack together as nicely. These don't compress as nicely. We have these chains hanging off willy-nilly. Then these things are going to be liquids at room temperature. So unsaturated fats tend to be things like olive oil, oils in general. Okay, veggie oil, canola oil, those are all liquids at room temperature. Again, some of them are better for you than others. Some of them have more saturation than others. So some of them have some solid characteristic. Take coconut oil, for instance. Coconut oil is fairly solid at room temperature, so some of its fatty acid chains are more saturated than others. It's still an oil, and so it's still going to have some unsaturated pieces to it, but there might be some combination of the two. Okay, and all fats and oils are going to have that sort of blend. These are just generalized terms. Okay, so that's the cis conformation. Now, if we were to artificially bend these things into the trans conformation, okay, so if I was to take this thing, I'm going to use a different color here, and flip this thing around. So if I flip this thing around and now I have straight chains, and I flip this thing around and now I have straight chains, and I flip this thing around and now I have straight chains, then my blue here that I've indicated by kind of showing that flipping of the cis to the trans conformation is going to give me something that looks more like a solid at room temperature. So the blue here is in the trans conformation, and we call that a trans fat. Trans fats, and you've probably heard that trans fats are not very good for us because this is an artificial process. Our body doesn't process these very well. It processes it well in the cis conformation. That's what we're used to. That's what We've been giving it for a long time, but they've gone through and done this, it's called a hydrogenation process to flip these things around, and that gives you these trans conformations. And these trans fats, or hydrogenated fats, which you might have also heard of, will cause these to be more solid at room temperature, and straighten out these kinks. And these trans fats, an example of these would be margarine. So in straightening out those kinks, you get a longer shelf life, you get something that's more easily made, you take something that's kind of healthy for us, oils, unsaturated fats tend to be healthier for us, and make it unhealthy for us, more challenging for our bodies to break down, and they build up more easily because they're solids at room temperature, and because they like to stack together better, because we've taken these things that our body processes better and that move through us easier and made them less so, okay, for lots of different reasons. So that's just kind of the skinny on fats, if you will, and about trans fats in particular. Okay, so the other type of lipid molecule are these steroids. So we've talked about fats, now I want to talk about steroid molecules. So steroid molecules are made up of a fairly distinct feature, and it's 4 fused ring structures that make up the backbone. So all steroids have in common this 4 fused ring structure. And again, I'm doing this like a skeletal diagram. So each of my corners here represents a carbon. And this is just the backbone. It could have stuff hanging off of it. So this is a 6-membered ring, a 6-membered ring, a 6-membered ring, and a 5-membered ring. And this is the backbone that is in common to all steroids. Okay. The one that we use in humans to make all of our other signaling molecules and other steroid molecules is called cholesterol. Cholesterol. And the OL ending here should make you think that one of the functional groups that's off of it is going to be an alcohol group, and you would be correct about that. So I'm going to draw this cholesterol molecule. It's a bit of a bear, so bear with me. And all of these guys are going to have this 4 fused ring structure in common. So this is always going to be the case with steroids. And then from there, the stuff that makes it different are all the functional groups and the things that are sticking off the ends of it. So there's a methyl group, there's another methyl group. Off of this, there's some long hydrocarbons. Alright, there's my cholesterol. I always think it kind of looks like it has an antenna on the top of it there, hydrocarbon antenna. So here's cholesterol. You can see that it has the functional group, the alcohol, that's over here in the corner. This particular ring is the one that tends to change functionality of this particular molecule. And then the part up here can do some interesting chemistry as well. So you'll see a lot of different molecules that have most of these features in common, but have something different down here and something different up here. So this is cholesterol, which is used to build all of our other hormones. And our hormone molecules allow for cell signaling and other type of characteristics and features. So if we talk about hormones, then one of the hormones that we can make from cholesterol is testosterone, which is the male sex hormone. And it looks like this. It's got the 4 fused rings. I always tell my organic students and biochemistry students that they get really good at drawing hexagons by the end of the year. And you guys are just getting a little taste of it here. Okay, now that you know a little bit more about functional groups, the ONE ending refers to the fact that there's a ketone present, and the ketone is down here on this last ring. This is my ketone functional group. And I also have an alcohol functional group up here. and that allows for it to do specific type of chemistry, of course. Testosterone is the male sex hormone, which is responsible for the secondary sex characteristics in males. So if we're talking about secondary sex characteristics, we're talking about things like facial hair. So during puberty, as we ramp up the production of hormones in our bodies, then for males, testosterone increases and you get facial hair and you get a deepening of the voice. You get a greater amount of body hair. You tend to be able to develop more strong muscles. You can get better muscle definition and development as you go through puberty. So that's testosterone. Now, I always like to compare testosterone to one of the female sex hormones because there's not a lot of difference structurally between them. So it's kind of an interesting comparison. So I'm going to try to keep that off to the side while I'm drawing this other one here. So here's, this is called estradiol. This is a female sex hormone. Estradiol. So if you have kind of testosterone to one side and estradiol to the other, you can kind of see those there. And then you'll see that there's an alcohol group that's in common on that 5-membered ring. The methyl group is in common there. And instead of the ketone down there that gave testosterone some of its functionality, this is called estradiol, di referring to 2, the ol referring to the hydroxyl group or the alcohol type ending. And so we have a couple different functional groups here. This is an alcohol group, but because this alcohol is attached to a benzene ring, this makes this a phenolic group. It's a phenol. Okay, so that's a benzene ring with an alcohol on it, and that's my estradiol. So this is the female sex hormone. Which, in terms of development, when females go through puberty, then this allows for things like menstruation, development of breasts, it allows for things like keeping our voices higher. So we have higher voices. It limits the facial hair that we have. This is part of the reason, so as women age, we go through a process of menopause. So once we no longer menstruate, we go through menopause, and our production of our female sex hormones goes down slightly. And when that female sex hormone production goes down, then different changes will start to happen. And one of the things that you'll see as women get older is a production of facial hair. So you tend to see old ladies with a little bit of facial hair, a little bit of mustache action. And usually that's post-menopause because you're not producing as many female sex hormones to help keep that regulated. So that's one of those things that you'll notice. So these are just a couple different hormones. Hormones are involved in a lot of different things, and steroid molecules in general tend to get a bad rap because of anabolic steroids. And anabolic steroids are the ones that bulk you up muscle-wise, and they're the ones that are abused by some athletes that are trying to get ahead in the game or whatever. But steroids in general have a lot of different purposes, and most of them are signaling and have to do with things like development and mood and all those kinds of things. So this is just a little bit of an introduction to the features that they have in common, these 4 fused rings and fats in general. So if you want to make some broad generalizations about them, so lipids in general are all nonpolar for the most part. They could have features that have polarity like these hydroxyl groups, but in general they're nonpolar molecules, which means that they don't mix well with water, like dissolves like. So lipids like fats and oils don't tend to mix well with water for that reason. So they're nonpolar molecules, and they have varying degrees of melting and kind of boiling depending on what all's in them and what all their functions are and what all their functional groups are. So, and the stuff hanging off of your steroid molecules is going to give you information about the way that it's going to interact in your body. So if you want more detail on that, please don't hesitate to ask. If you have any questions in general, then you know where to find me, and I'll talk to you again soon.